So Yiming will tell us about orbital selective superconductivity in Ruddlesden copper nickelates. And that looks great. That looks perfect. Uh, okay, this is the right screen. Yeah, the floor is
Yeah,
yours, Yiming.
yeah. Thank you, Ming. So, can you see my pointer here?
Yes,
Okay,
everything.
great. Yeah. So, yeah, I would like first to thank the organizers of the eQMA workshop for kindly inviting me to give a presentation about our most recent works about the nuclear superconductors. And my name is Yiming Wang from Rice, and my title is Orbital-selective superconductivity in Ruddlesden copper nickelates. So I would like to first thank all my collaborators for these wonderful collaborations. And yeah, so as you may heard from the previous talks, and it all starts from the recent discovery of this nucleate high TC superconductivity in 2023. And for this bilayer nucleate 327 material, the TC reaches 80 Kelvin when at high pressure. And also, I learned from the previous talks that this TC can also be enhanced to up to 96 Kelvin upon doping. And also, this discovery sparked a new wave of study in this nickel-based superconductivity family. And more recently, there are also other materials in this family that also exhibit this unconventional superconductivity at high pressure, like the 4310 and the 5311. So yes, so for the in the inside this 327 material, there are three electrons occupying the four active orbitals. So if we want to consider this bilayer as within one unit cell. And this multi-orbital physics is similar to the ion-based compounds, but it is distinct from the single-host systems like the infinite layer nickelates. And I would also like to note that these this 327 material exhibits very strong orbital selectivity as is revealed by the RPAS in the sense that the bandmass observed in experiments for different orbitals behave differently. And this leads to is my outline for this talk. So as first, I will talk about the concept of the optical selectivity as which serves as a multi-orbital correlation effect. And then I'll talk about the correlation effects and the orbital selectivity in the bulk and the fumed superconductor 327. And after that, I will talk about the orbital selective superconductivity in 327 material. And last but not least, I will also present our most recent work on the correlation effects and orbital selectivity in tri-layer 4310 material. So, so basically, in realistic systems, there are like basically usually the multi-orbital correlated systems. And for these multi-orbital systems, different orbitals under electron interactions in general exhibit different quasi-particle weight. And away from Hall filling, the extreme case is the orbital selective Mott phase. And in some sense, in this case, the some orbitals in the system remains metallic, where the quasi-particle weights are non-zero. But in some other cases, these orbitals behave completely Mott-like, and the quasi-particle weights are zero. And in spectroscopy experiments, these orbital selective behavior can be observed through like RPAS for by observing that the different orbitals require different quasi-particle mass. Yeah. So so we first I would like to note that this bilayer nucleate 327 is a canonical orbital selective system. So let us first look at this phase diagram. And at low pressure, at high temperature, it is established that there is a spin density wave. And when the temperature is lowered, there is a it enters into another density wave, and the nature of this density wave is still under intense investigation. By applying pressure to high pressure, then there is a superconductivity emerging. So, and recently there are some optical conductivity measurements that reveal that the measured joule weight is lesser than 10% of the joule weight obtained from DFT. And this indicates that the correlation effect in the 327 material is as strongly correlated as the classical cuprate systems. And also, RPAS revealed that in this system, there are strong orbital selective tendency that for this DZ orbitals, the quasi-particle mass, the mass enhancement is stronger than this mass enhancement in the x squared minus y squared orbitals. And more recently, people have successfully synthesized a thin film version of the 327 material. And they find that the superconductivity emerges even at the ambient pressure. And this thin film superconductivity was talked in this previous talks. So, so So with all these observations, we began to investigate these systems theoretically using a bilayer two-orbital Hubbard model with a strong bonding in Z-square orbitals. And this orbital was first introduced in our this model was first introduced in our 2023 paper, and we used the slave spin and the Gutzwiller to study this correlation effect. So here is a brief introduction of our theoretical method. So we basically re-express this physical electron d electron in terms of the slave spin operator and the spin operator. And the slave spin operator carries charge degrees of freedom, while the spin operator carries spin degrees of freedom. And there is a on-site constraint that for this spin operator and the spin operator to satisfy the correct Hilbert space. And we also utilize this rotation invariant Gutzwiller method to cross-check with our slave spin result. So here is our result for the quasi-particle weight for different orbitals under correlation effect. We find that as the Hubbard interaction U is turned on, it is the anti-bonding Z orbitals that is most strongly correlated, and then followed by these bonding Z orbitals. And the least correlated orbital is the x squared minus y squared orbital. And we also find that when we increase the filling of the system, the correlation effect becomes stronger. And ultimately, when you reach the Hall filling of the system, then all the orbitals exhibit mode transition at basically U equals 4 eV. And so we also calculated the effective band mass under correlation effect, and we compare our result with the RPAS measurement. And as is revealed by the RPAS, so it is this Z-square orbitals that has the strongest mass enhancement compared with the x squared minus y squared orbitals. And our theoretical calculation at U equals 6 eV matches with these experimental results in the sense that this Z orbitals has the strongest mass enhancement and followed by these x squared minus y squared orbitals. And so from our previous calculation, we established the fact that the Z-square orbitals are in the proximity of the multi-insulator. So there should be a very strong spin singlet interlayer correlation. And we capture this strong spin singlet antiferromagnetic correlation by introducing this antiferromagnetic Heisenberg exchange coupling. And then we find that under this spin singlet correlation, the bonding and anti-bonding bands are splitted further. And this splitting is compensated by this shrinking of the bands toward Fermi level under strong no, electron interactions. And this will lead to a direct implication to the optical conductivity results. So we provide a calculation of the optical conductivity under electron correlation. And we find that first, the Jude weight is reducing under strong correlation. And when U equals 6 eV, the suppression is around 0.4 compared with non-interacting one. And we also find that for this interband and the interband peak basically remains at around 1 eV, even though the electron interaction is strong. So this is because the antiferromagnetic interlayer correlation compensates for this strong suppression induced from the electron correlations. And we also calculated the optical conductivity along the sigma z directions, interlayer directions. And we find that this if this z-square bonding band is below the Fermi level, which is as indicated from our calculation, then there will be also a strong interband peak and also emerges at around 1 eV. Yes, and after introducing our like correlation effect in this material, we utilize this correlation effect to study this superconductivity in this material. So we construct a effective TJ model where the non-interacting part now are addressed by correlation effect with non-zero quasi-particle weight Z. And then the interacting part is the Heisenberg spin exchange coupling, where the J perp corresponds to the interlayer coupling, while the J parallel corresponds to the intralayer coupling. And yeah, here is our phase diagram for different for the superconductivity channels. And we find that when the interlayer spin exchange coupling is small, then the ground state is formed by the D-wave pairing, which is within expected because in this limit, it's effective as single layer physics. And interestingly, when the interlayer coupling becomes strong, then the ground state is formed by the S-wave pairing. And depending on the relative interaction strength of the interlayer exchange couplings for these x squared minus y squared orbitals or the z squared orbitals, this S-wave can be contributed predominantly by either x squared minus y squared or z squared orbitals. And we also note that for these S-waves, they are all anisotropic, although they are all fully gapped. So our result also provides some insight into the superconductivity in the 3 to 7 films. So as you heard from the previous talks, so whether the gamma band crosses or not crosses the Fermi level is still under intense investigation. But I will provide one scenario in the case where the gamma band is crossing the Fermi level. And this crossing was already reported by Professor Chen's talk yesterday. So, and when the gamma band is crossing the Fermi level, so we find that it is the S wave is contributed predominantly by these Z square orbitals. and then followed by this small amount of x squared minus y squared orbitals. And the ratio of these two is roughly 2 to 1. So then we calculate the gap function along at the gamma band. And we find that so the beta band is formed predominantly by these x squared minus y squared orbitals as indicated here. And especially when we scan the band through this theta angle and along this diagonal direction, the beta band is solely contributed from the x squared minus y squared orbitals. But interestingly, when we look at the gap function, and the gap function is mainly contributed by these z squared orbitals. And so if you combine this optical content and the gap function together, this will lead to a local minimum at a diagonal direction. And we also calculated the gap function along the gamma band when the gamma band is crossing the Fermi level. And because the gamma band is solely contributed by the z square orbitals, so the gap function is basically composed of these z square orbitals and it's isotropic in the Brillouin zone. Yes, and our results are consistent with this recent ARPAS measurement of this two gap feature, where you have probably heard from Professor Chen's talk yesterday that this gamma band in experiments also exhibit a local minimum. Sorry, the beta band also exhibits the local minimum, whereas this gamma band remains its flat feature. Yeah. And we also plotted this density of states for this superconductivity. And our result is also consistent with the recently observed STM measurements, which also revealed a similar two-gap structure. So yeah, last but not least, I will talk about our most recent work on this tri-layer 4310 material. And this was first observed in 2024, where at high pressure, the TC exhibits 30 Kelvin. And so in this tri-layer system, so there are 4 electrons occupied in the 12 active states. And there are also optical conductivity measurements that reveal that this observed joule weight is basically 1/3, 30% of the joule weight obtained from the DFT. And this correlation effect is similar to the iron-based compound, especially this barium 122 material. And also, ARPAS exhibit the orbital-selective tendency, where the quasi-particle mass of different orbitals exhibit differently. And in our calculation, we performed a slave spin calculation on the tri-layer two-orbital Hubbard model for this compound. And we find that when the interaction strength is turned on, also the quasi-particle weight decreases, and it is the d square orbitals in the 2 outer layers that is most strongly correlated. And in this sense, we conclude that the correlation effect in this 4310 material is weaker compared with the 327. This is consistent with this also the experiments. And we also calculated the optical conductivity. And we find that under electron interaction, so the suppression of joule weight at U equals 6 eV is 70% compared to the non-interacting one extracted from the DFT. And within that, let me combine all our uh, theoretical investigations together. And we find that since we established the connection between this filling density and the correlation effect, basically we find that because the 4310 is even far away from the Hall filling compared with 327, and the correlation effect is weaker. So we place this 4310 to the left-hand side of this 327, and both results for the two materials matches within a single unified global phase diagram. So yeah, within that, let me uh, summarize our conclusions. So we first established the global phase diagram of the interaction strength and doping for the multi-layer nucleus, both for 327 and 4310. And this provides an overall perspective of the optoselective correlation effects. And it also allows for the construction for the multi-orbital TJ model for superconductivity in the optoselective band metal regime. And our results for the orbital-selective correlation effect provide understanding for the RPAS and the optical conductivity measurement. And specifically, the bilayer and the trilayer nucleus has similar correlation effect like the optical selectivity. And the trilayer compound is less correlated compared with the bilayer one. And also, we provide our understanding for the superconductivity for the 327 material. And with our calculation, find that there is a rich interplay between these inter and intralayer effective interactions. And then this will lead to the competition between this extended S-wave pairing and D-wave pairing. And also the crossing of this square bonding band will lead to implication to the recent experiments. So that's all. Thank you for your attention.
Thank you very much, Yiming, for this very clear talk. Any questions from the audience? Oh, there is one in the chat. Bear, do you want to? I can beat this out unless you want to ask. There was also some ARPAs yesterday from the Stanford group which suggested the gamma band does not cross the F in strain film. Do you have any idea what could contribute to the different reports? Or
Yeah, I would say this whether the gamma band crosses or not crosses the gamma band is still under like also investigation in experiments. So we theorists, especially in the early stages, we just provide some understanding on the case where what happens if the gamma band is crossing the Fermi level. And we also have the result when the gamma band is below the Fermi level. In this case, we find that there is no like minimum, a local minimum. Instead, there is a local maximum, and the gap function along the gamma band, the beta band is something like this. And yeah, but we're still waiting. We're still waiting for the clear experimental investigations.
there's a second part of this question. From theory, have you studied, for example, how the band alignments change as a function of U or other parameters?
Sorry, which one changes with the U?
The same band. So this is in her second part of her question, whether the band alignment or band position changes as a function of U or other parameters.
Uh, the band position. So I think so the band position you mean this
Gamma band. I assume this is because it's the same question.
oh
Yeah.
yes.
Sorry, like the maximum or the minimum of the gamma band. Like I mean, if you can, we've seen some calculations with Hubbard U and some without Hubbard U. Have you looked more explicitly at like how some of these other parameters in the DFT or the first principles calculations can like shift these band alignments?
Oh
just
yes.
up or down?
Yeah, that's a good question. So I think in our case especially in our calculation, we are tuning the energy level between the bonding and anti-bonding z-square orbitals. So when we say the gamma band is crossing the Fermi level, we are tuning these relative energy levels to be in this value, whereas the parameter in this bulk system is at the left hand side. Yeah, so maybe this energy level is the key for is a key parameter for this behavior.
Okay, Mike, have a question?
Yeah, in reference to Barrett's comment, this actually goes back to a comment that George was making the other day. When we use these band description, we should be careful. So there was a Presidentium 4310 ARPAS paper that appeared on the archive last night, and they clearly show that the z-squared orbitals look to be completely incoherent in ARPAS.
Yeah.
In that case, compared to some previous results. So sort of like the only coherent like features seem to be associated with the x squared minus y squared orbitals. And that seems to be consistent with the fact that you see in-plane density wave modulations in these materials. So should be kept in mind, when we're thinking about, how far can you go with a band-like picture?
Yeah, okay. Thank you for your comment. Yeah, so I would say in our calculation, we at most captured the correlation factor within this psilocybin. But as you said, yes, the incoherent feature is still under investigation. So we probably leave this inclusion into the future work.
Ming, can I just chime in on this? Uh, So, so I think actually this new work showing up on the archive last night, it's actually very interesting in the sense that you could interpret the z-square being incoherent as the result of interactions.
Absolutely.
So that would suggest that even for 4310, in which we probably all agree that the degree of correlation is not as strong as the 327 bilayer case, even in that system, there is a strong enough interaction effects to drive the z-square orbital to look like incoherent, at least in the Prasadimian case. So
Exactly.
to me, it's a very exciting development.
Great. Any other questions? If not, we will thank Yiming very much for your very nice